Okay, so our topics, we're going to start with our AFL. So if you don't have that in front of you, will you grab that out? And I'm going to write out some of this information on the board so we can reference. And when we go to solve for that. Yay. So it says, what is the molar enthalpy of reaction? That's a question I've gotten a couple times, is the difference between molar enthalpy, like what does that mean exactly? And so I think that's a good differentiation to understand. We will deal a lot more because we like kind of touched on thermochemistry during this unit. And then we're going to come back in the spring when you come back from winter break to learn about kinetics. And so we're going to talk a lot more about molar enthalpy, but essentially our Q value that we've been solving for, that's going to be solving for amount of energy, and that's going to be for any given reaction. So that's your energy in your reaction. So it's joules, or obviously it could be kilojoules. A lot of times we'll switch it to kilojoules. And so then delta H is going to be a constant. It's going to be consistent. So you could use your joules from a reaction, but your delta H is always going to be your joules or your kilojoules, and then it's going to be per mole typically. So we would call it your molar enthalpy because it's basically your number of joules per mole. So you'll see if you needed to solve it, you would take the Q that you found. You did this in the lab that we did. You took the joules that you calculated in your equation. This was the last thing you did on part 2. And then you divided it by the number of moles you had in your reaction. So it's kind of the difference between those two. I've had that question asked a couple times. Just what is molar enthalpy, kilojoules per mole? So that's what all these values are here. So you didn't really necessarily need to know that for this particular question. I just wanted to throw it in. So it's asking for the combustion of methane based on the bond energies for your various bonds in your reactants and products above. So they're not giving you a balanced equation. Your job is to write the balanced equation. Step 1, that's first. Step 2 is it's a combustion reaction of methane. So you got to know what methane is. So meth prefix means how many carbons? 1. And so if we have only 1 carbon, it has to make how many bonds? 4. So if methane has to be CH4. So that's first. If you were given any sort of organic compound, you'd have to be able to draw that. That's a pretty simplistic one. I would feel like any ones I'd expect you to come up with on the test are going to be pretty simple, kind of the same deal. Then it's combustion, so I'm going to react methane with oxygen. And then it's going to make CO2 and water. Okay, so that would be writing my reaction. Are there any questions on where that information came from? Okay, step 2 would be we have to balance our equation. So you can't ever have an equation without it being balanced. I have 1 carbon here and 1 carbon here, so that's already balanced. I have 4 hydrogens here and 2 hydrogens here. So I'm going to put a 2 there in front to take care of my hydrogens. That leaves me only with my oxygens. And you have to remember I have 2 oxygens here, and I also have 2 oxygens here. So that's a total of 4 oxygens. So I'm going to put a 2 here in front, and that'll make my equation balanced. So far, so good. Then the last step before we can actually total our values is got to be to figure out where our bonds are situated. So we're going to have to draw our Lewis structures. So once again, if you are not quite on board with Lewis structures, that's definitely something you're going to have to spend your time doing this weekend. So CH4 is going to have 4 carbon-hydrogen bonds. Your oxygen, it has 1 central atom, or it only has 2 atoms total. So you just pick one of your oxygens to be a central atom. I usually do the one on the left. And then you would add your electrons around the outside of the other. 2 oxygens mean I have a total of 12 electrons because they're each 6. So I've already used 2 there, 4, 6, 8. Obviously, we knew we had to get that to 8. So that gave me 4 extras. So I'm going to put those 4 on my central atom. But now that one only has 6 electrons. So that's going to be a double bond. This is a Lewis structure you're probably going to draw a lot in your life. It's one that's probably worth your time to just be good at having memorized, or whatever that may be for you. Then you either have to just remember that there's 2 of them. Some people just putting a 2 in front can kind of remind you. Time-wise, it's not a lot of time on a multiple choice to draw them all out, but it didn't take me very long. And then carbon dioxide is another one that is probably worth your time to have memorized. I only have 1 carbon dioxide in my reaction. And then water, once again, it's worth your time to have memorized. That one, a lot of you have told me you do have memorized. So I have 2 water molecules because I had a 2 in my coefficient. Questions on anything I did with my bonds there? So far, so good? I could draw one of these out more specifically if you're not sure about. Questions? All right, so this is going to be my dividing line. Everything to the left are going to be broken apart, and everything to the right is going to be added together. So this means this is energy that's going into my reaction, and then this is going to be energy that's coming out of my reaction. So the first thing I'm going to go through is total up my values. And so my chart, I'm going to reference the one on the lab. I'm not going to rewrite all my numbers. So I want you guys to just kind of follow along with me. So here, how many different bonds will I have to break that are carbon-hydrogen bonds? 4. So I'm going to have 4 times my carbon-hydrogen amount, which is going to be 400 kilojoules per mole. And I'm also breaking 2 double-bonded oxygen atoms, because I have 1 in each of my molecules. So oxygen is 500 kilojoules per mole. So I would find my total of those 2 values. We could go ahead and do that now. So 4 times 4 is 16. So 1,600 kilojoules plus 2 times 500 gives me 1,000 kilojoules per mole. So when I add those 2 values together, I'm at 2,600 kilojoules per mole. Then if I come over here, I'm going to do the exact same process again. So I've got 2 of my double bond carbon oxygens. So I have 2 times 700 kilojoules per mole. Plus I have now, do you see kind of drawing it out? It helps people if you're forgetting that that 2 is in there. But I have a hydrogen-oxygen bond there, 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 and there. So that's actually 4 times whatever my hydrogen-oxygen bond is, which is my 420. So far, so good. Questions on what I've done so far? No? Okay. So then I'm going to sum these together. So if I have 2 times 700 is going to give me 1,400. And then 4 times 420 gives me 1,680. Correct? So far, so good. And so then if I total my sum here, what do we get if we had 1,400 and 1,680? And then what do I do with these 2 numbers, 2,600 and 3,080? Subtract. Do I take 26 from 30 or 30 from 26? This has to be my negative number because remember they're going out of my value. So 26 minus 3080 is going to give me negative 480. So that's my answer is B. I ran out of space here though. Questions on anything I did there? Your math, you'll notice, was a little bit easier to multiply there. We don't have like 1s in there. That kind of makes our math a little bit simpler, but some of them got a little bit tricky, potentially, depending on how good you're at doing math in your head. Let's move on. Mackenzie.
Would it potentially ask you what it is in joules in the test too? Like, would you have to convert from kilojoules to joules, or would you have to do that?
I mean, that's always a possibility. If you had to convert from kilojoules to joules, you might have to do that. But where you would, I would.
I remember really
You had to do that on one of your multiple choice problems. It gave you on number 8. Oh, that was liters to milliliters. And then I know on the FRQ, you had to do that. Number 8, you actually had to go from, it gave you the number of liters in the pot. You had to convert that to milliliters, so you knew your number of grams. That's when I was thinking it from multiple choice. And then on the FRQ, the second FRQ, 2A came out in joules, and 2C needed it in kilojoules, so you had to do your conversion there. It's definitely possible, and you should know that 1 kilojoule is equal to 1,000 joules, so that if you did need to make that conversion, you'd be able to do so. Yes, ma'am.
What did you say? Why do we have to subtract the first number and the second number?
This is the amount of energy that's leaving, because when you form bonds, you're releasing energy. And when you release energy, then we show that as a negative sign, because that's energy that's leaving your system. And when we're putting energy in, like when you're breaking bonds, you always have to put energy in. And so kind of that's an important differentiation you should make, is that breaking bonds, we have to use that energy, because remember, our atoms were sharing. When they share their electrons, they're at the lowest energy configuration. Now, in order to break them out, you have to be moving them to a higher energy configuration. So you have to provide that energy to the atoms for them to be able to break the bond. Whereas now, when I bond them together, you're moving them from the higher to the lower energy configuration. They don't need that energy anymore, so they release it. That's a really important distinction that you should be able to make. Questions on it? I'm going to move on then. Sound like a good plan? I'm going to erase this. All right, so next up is, I might come back to organic. Let's talk about bond energy and their graph and do some Lewis structures and such. Okay, so the whole idea behind bonding in general, yes, sir.
Sorry, on that
No, you're
last
fine.
question, it's not like about the calculations or anything. It's just like when, like, so if you're gonna burn a bunch of methane, like if you're just gonna go outside and do this, where does the energy come from to break those bonds?
Well, if you think about any of your combustion reactions, and if you wanted to burn methane, you'd have to probably light a match or, do something. When we go to light our Bunsen burners, that's propane, that's a combustion reaction. So it takes a spark to get the bond broken in the first place, but it's just a small amount of energy goes in, and then more energy comes out.
Okay.
And so then it's able to kind of maintain itself because it's producing energy. That's a good question. Any other questions that came about? Okay, so I think that the question you were asking me, Mira, was about this graph picture guy there. And so we were looking at our potential energy over here. And we looked at, well, that says energy. We were looking at 2 hydrogen atoms. Those are very fun. And so we were talking about the importance of understanding the distance between our 2 atoms. So if we were to be looking at bonded pairs, we have a relationship between your 2 different sets because they both have electrons. And we know the electrons of one hydrogen are going to be basically repelling the electrons of your other hydrogen, right? So they're constantly pushing each other apart. But you also have the electrons on one hydrogen that are being attracted to the positive protons of your other hydrogen. So they're being pulled together. And so if we think about this as being a push and this here being a pull, you have to, that's always going to be counteracting each other, right? And so if you get them too close together, then those pushing forces are going to be too great. And that's going to require a lot of energy to maintain those atoms really, really close together. If you get them too far apart, then trying to overcome that pull is a lot harder too. And so there's basically like this graph here is showing you the ideal distance between your 2 atoms so that you've minimized the repulsions between your electrons while also maximizing your attractive forces between your positives and your negatives. Because if they're too far apart, these guys can't attract together and they won't bond. And if they're too close together, those electrons just require so much energy So that's why our potential energy is really, really high up here, because it's going to take a lot of energy to put them close together. So you want to find where that lowest energy, kind of the perfect middle ground. So then we have 3 different types of bonds that we talked about. We have single bonds, double bonds, and triple bonds. That's in this category is where we also talked about that. And so having a single bond means we just have 2 electrons that are being shared. Double bond, we have 4, triple bond, we have 6, right? So the more electrons we share, how is that going to impact the distance between our atoms? They get closer together with more electrons or further apart with more electrons? Let's get closer together. Think about our Coulombic attractions. If we have positives and negatives, they're going to be attracted to each other. So the more negatives we have, the bigger attraction it's going to be. So the triple bond, they're going to be very close together. So this is what we would say is the shortest of our bonds. So they'll be the closest together. So then my single bond would be the longest of our bonds. Those would be the farthest apart. And then obviously the double bond would be in the middle of those 2. So then between single, double, triple, which do you think is going to be the strongest, be the most difficult to break? Triple. This is both the shortest and the strongest. So it's going to require more energy to break. And you would see that when we were doing our bonds, you would have, we didn't really have any of the similar ones to compare, but hopefully you saw that they had a little bit larger. So this is going to be weaker. It's a little bit easier to break a sigma bond. Do you remember that a single bond is called a sigma bond?
Yeah, we do.
Now we do. So that's our sigma. And what do we call it when we have a double and a triple? Pi. So in a double, you'd have 1 pi bond and 1 sigma bond. And a triple, you'd have 2 pi bonds and 1 sigma bond. Sigma is a single bond. Pi is, a double bond has 1 pi and 1 sigma. That's how you get the 2 bonds.
But I'm thinking of, so sigma is at the one line, if you're drawing a fluid structure?
Right. So like this would be a sigma bond, and then the one on top would be a pi bond. So a double bond has 1 of each.
Oh, so triple bond would it be 2 pi and a sigma or 2 sigma?
1 sigma. So anytime you have 1 bond is 1 sigma bond. And then you have 2 pi bonds.
So really, no matter what, you're only going to have 1 sigma.
Yeah, you'll always have 1 sigma. And then go from forward adding your pi bonds. And if you I can't, you guys just don't. This is why there's only 1 electron domains, because the sigma bond is going to be your connection between your 2 electrons, and the pi bonds actually behave slightly differently, but it's beyond where you are now, so I won't say anything else. Okay, so that would maybe be everything I think is pertinent to that particular topic. Are there anything else you guys would like to know about that? Any other questions here? Don't be afraid. This is time to ask questions.
Which one was the ideal one on the graph again?
This
The
one,
lowest one?
because it has the least, so you're minimizing your potential energy.
Okay, so this one.
Oh, so the one on the right is not. Yeah.
Right. Because those both have greater energy. Remember, atoms are lazy, so with least amount of energy. Okay, I'm going to go away. This.
My ears are not fine-tuned.
Is there anybody who has a particular Lewis structure they would like me to do? Yes, ma'am. Do what? So NaCl is going to be an ionic bond. And so for NaCl, if I were going to draw a Lewis structure, you would draw Na with just a positive charge showing no electrons around the outside. And chlorine would have all of its electrons around the outside and like this one extra one that had come from sodium. And it would have a negative charge. And so that would be as much as you could draw for a Lewis structure on that one.
So ionic
Yeah, because in a covalent, we don't typically bother with drawing Lewis structures for an ionic bond because you're always going to have your positive one with no electrons around it and your negative one with all your electrons around it. And then you guys know your charges, you know?
Yeah.
So mostly we draw the Lewis structures because how they share their electrons is much more complex in a covalent bond. So since ionic, you're typically just transferring your electrons. We leave it at that and focus on covalent for Lewis structures. No, you're welcome.
Okay, on the worksheet that you just gave us, there's one example that has SO2 and it has like a double bond and a single bond, and just kind of like wrapping up the sigma pi thing. I just wanted to like clarify and make sure that there's like, I understood there would only be like 2 electron domains, but there would still be 2 sigma bonds and 1 pi bond.
Yes,
Oh, all right.
you're exactly right. I think SO2 is a great one to do. We can look at SO2 maybe as a group for SO2 because this is one that people look at and want it to have a different Lewis structure than it actually does. So that's a good place to start. I'm going to come up with one anyway. Is anybody going to be upset if we do SO2? All right. So SO2, if you go to look at the way that it's set up, I mean, we're going to initially put it at S and our O's. Why did I put S in the middle? It's my central atom. It came first. I only have one of it. You know, any of those are good things to say. So for oxygen, sulfur, and oxygen, how many total electrons does that provide me? How many? Did you say
18.
18? I thought you said 14. 18 is correct. I'm sorry. I just didn't hear you. That was all it was. I was just asking. But 18 is right. So if we've got 18 electrons, our first step in building Lewis structures has to be to make sure the outer electrons, or pardon me, the outer atoms, my terminal atoms, are at their lowest energy configuration. So we have to get those all to 8. Once you get those to 8, then it's easier to share your electrons with your central because he's got more connections going on there. So I'm going to start with adding 6 electrons to my oxygen, not because it had 6 valence electrons, but because I want it to be at the lowest energy configuration. So now it has 8 total electrons. I'm going to do that on both sides. So now both of my oxygens are at their lowest energy configuration. Am I done? No, because sulfur is not. It is only currently sharing 8 electrons. 4 electrons. We need to get it to the 8 electrons. So I'm going to need to do something else. Before we go to share, we have to make sure we don't have any extra electrons here. Since we've established there's 8 and 8, I've only used 16 electrons. So I have 2 more that can go somewhere. And those 2 can be put on my sulfur. Cole, is that what you're going to yell at me?
No.
Oh, do you have another question? Okay. So I have 6 electrons now. It's closer, but still not great. So what am I going to do to finish that? We got to share. It doesn't matter right now which oxygen we share it from. So pick one and create a double bond. And now we have a double bond on one set of my oxygens, not the other, and that's perfectly fine. So if I were going to draw the correct, like the perfect Lewis structure for this, I would really have to draw 2 Lewis structures. Remember, we call those resonance structures, where we show that you could represent this structure both ways with a double bond on this oxygen. And so that resonance structure is representing the fact that that oxygen double bond actually will be traveling back and forth between your 2 sides. And so this can show resonance is the word. Resonance.
Do we have to do
If you're asked to do that, you have to do that.
So let's say back here, we can state that new structure is
How would it word it in the question?
I could see it being like a multiple choice question that said which one of these would show resonance. And if you had something that had like a double bond on one and not on the other, that would be the one. I think I've seen it on an FRQ, like, why is it best represented to show as having more than one resonance, you know, like those kinds of questions. It's not a huge topic. I'm not super worried about you guys knowing that right this moment, but it is something you need to be aware of and understand. If you heard about resonance, it can't shock you. So those kinds of things. Mostly, I'd like you to be prepped for the AP test for that. So I'm going to go forward and talk about polarity and all that jazz that goes with this. But before I get there, do you have other questions on how this happened?
Yeah, situations and structures where you have more electrons than you should have. Like, say we were supposed to have 18, but we actually have 24 or something.
No.
So if that ever happens, that's just kind of like.
Yes. Because where would those electrons have come from?
Yeah.
Yeah, it must have been just, I keep getting too close to my smartboard. That would be my guess. Yes, you can. I think that's a great idea. So one thing just for whatever that works, NO3 like has a -1 there. If you have a charge to that, that can give you more or less electrons than you would have maybe seen with just NO3, because that -1 is showing you have extra electrons. That could be maybe a place that applies, but otherwise no. Any other questions about drawing of the Lewis structure?
Just for example, like on SO42, would you want us to draw up the bracket around the Lewis structure and write?
Oh, SO4 to negative.
Or two negative?
Yeah. Yep. I was just confused what you're talking about for a second. But yeah, you're exactly right. I would want you to put a bracket in there if you were asked to. I don't think so.
Yay.
Not on my test. I think it's a good thing to know for your AP test. Your formal charge is a good thing to have if you are worried about your Lewis structure. It's a great way to check your Lewis structure. So maybe when you finish your FRQ, if you have to draw a Lewis structure for that, it could check your work on that. But it's not something I'm going to expect you to do. Okay. All right. So you guys were seeming a little worried about our sigma bonds. I know you were saying that there, but each of these has a sigma bond here, and that's our pi bond. So that's what she was talking about when we said that there's 2 sigma, and then that gives me also 1 pi bond. So that's how we would address that. Based on its total number of electron domains, how many electron domains does this have? So it is 3, because I have the lone pair on my sulfur, and then a single bond and a double bond. And remember, the bonds count the same whether it's a single bond or a double bond. And so I give me 3 electron domains, 2 of which are bonds. So what shape does this molecule make? It does. It does make a bent molecule. And what would be my bond angle for this particular one? And it's 120. Why is it 120 and not 80 degrees? I mean, 180. Did I say 120? Why is it 120 and not 180? That's what I meant. Because it's got 2 bonds. Yeah. So it's got 3. You have to triangulate your electrons to get them as far apart as possible. And anytime that happens, you're going to end up with your 120. And it actually is going to be slightly less than 120 here on one of your angles, because of the fact that you are pushing those oxygens and sulfurs a little bit together. It's not necessarily something I would, if I just asked you what the angle is, 120 would be a fine answer for that. If I then asked you some information about why is it slightly different, then I'd want you to explain lone pairs. Kind of understand the difference between those two? Yes, sir.
So would you accept 120 or less than 120?
Any other questions about this? Let's talk about hybridization for a second. So remember, that's a thing you have to know. And so for hybridization, it's going to be based on your electron domains. And since we're going to be filling your electrons all from the same energy level, you establish what orbitals are available to actually bond with. Just like text somebody during class, be like, I need help. So remember, in an energy level, you have 1 S, you have 3 Ps, you have 5 Ds. If that's shocking information to you, touch base with me later and I can explain that. But these are all from the same energy levels. So 1 S, 3 Ps, 5 Ds. And so there I have 3 electron domains. So I'm going to pick 3 orbitals to hybridize and make 3 brand new orbitals, so that when my electrons are bonding here, here, and here with their oxygen atoms that need to come in, we have equal energy locations to go. So my hybridization for this would be sp2 hybridized, because I needed 3 places for my electrons to go. So remember, S is always 1, P is 3, and D is 5. It goes in odd number increments, which is so nice to have. Hybridization. Next up is polarity. We prepared for that.
What'd you say? I didn't see
I'm going to talk about polarity next. Is there any questions on anything I've talked about yet? Okay. So then polarity, I'm going to use this one over here because I drew all over that one. When we're going to establish polarity, we have to look at our periodic table. And on our periodic table, figured I'd have one around here. I want to see how close my atom is to fluorine. That's going to have my highest electronegativity. So between sulfur and oxygen, which one would we say is closer to fluorine and has the higher electronegativity? Oxygen. So I'm going to draw my electrons as going away from oxygen. And the way that my molecule's drawn here, this looks a little bit like my electrons would be evenly distributed. Some going towards oxygen and some going towards my other oxygen, so they would end up canceling out. The way I drew it, it looks like it's a nonpolar molecule. But if you remember, we established it's really bent. So if you kind of think about it in terms of what your sketch would be for this, with my sulfur here kind of being on the top of my point on my line, and that causes my electrons to go out. So overall, my electrons are being distributed towards the oxygen part of my molecule, causing this to become slightly negative. And that would cause my top to become slightly positive, my sulfur end of the molecule. I shouldn't say top, because you can turn this any direction you want to turn it. So the sulfur sides will be positive, the oxygen side would be negative.
So since we know that the shape is bent, wouldn't that just mean that it's pretty much always going to be a polar molecule? Because if it's going the other way, wouldn't it also?
It would also be. That's true. And so that's why we said the two clues is to know whether it's going to be polar or not polar would be if you have lone pairs on your central atom, or if your outer atoms are different atoms, then you know the likelihood is it's going to be polar. But because you have a quick, easy to remember device like that, the chance of me just asking you, is this polar or non-polar, isn't very great. I'm probably going to ask you something more complex than that. Identify which side the charges are on, or compare two different compounds and see which one would be more polar or less polar, or things like that. So you'd be pushed a little bit further.
So, like, yes, the lone pairs cause it to be polar, but like the sides of the lone pairs isn't necessarily the polar side.
Correct. And I don't want you to think of it as the lone pairs are causing them to be polar, because that's not what's causing it. It is causing there to be a difference in shape, which leads to the asymmetry, and all of that's true. But lone pairs are just a tool for us to use to help us when we're trying to identify polarity. It is not ever something you would put in an FRQ as to why something is polar. The reason why something is polar has to do with your electron distribution. So you would say something about it being unevenly distributed, and you would need to be specific and say, on this particular molecule, the oxygens, due to the higher electronegativity, would have the electrons more often, so the electrons would be distributed more towards the oxygen end, causing an imbalance, or something along those lines. You would definitely not say the lone pairs. That's something that a lot of people do have a misconception about, so don't. Right.
So,
I think that's a great point to make.
So the lone pairs don't cause it to be any more.
Correct.
Okay.
Correct. The electronegativity is inherent to what the atom is. Other questions?
Wait, so you cannot like use the shape of it at all in your explanation of why?
You for sure could use the shape in it, because the shape is part of the reason why it has asymmetry. Because if this were linear, then it would have been. And so just that would be a fine way to too, but you just wouldn't want to leave it at the shape.
So for the one with like the sigma and pi bonds on the AFL, it's the NO+1.
Mhm.
I know it's Y, but would that count as one electron domain or two, since there's
That it has one sigma and two pi's, that would be one electron domain.
I know you just said this like 3 times, but what are the clues for polarity?
Clues for polarity would be lone pairs on your central atom, or your terminal atoms being different. But I tell you those as clues, not as words to put in your FRQ. Yes, ma'am.
Just as the electron domain. So like on SO2, so the double bond is one.
Correct.
One electron, and the other bond is another, and then the lone pair is one.
Yes. So the question was about electron domains and clarifying the fact that there are 3 because we have one lone pair, we have one that's a single bond, and one that's a double bond. So those are all examples of electron domains, and they each count as one electron domain. Other questions? Okay, so we've got about probably enough time to do one more topic. Would you guys rather it be organic, another Lewis structure like we did here, or the bonding types?
I feel like bonding type is just like
By bonding types, you mean like
like
ionic?
properties or
No, that's like.
I mean properties.
Oh.
We should go.
Bonding types would be the properties,
It's just the stuff on
Yeah.
the Venn diagram.
and knowing how to use those.
What do you mean?
Oh,
Yeah.
I think Lewis structures was the winner from what
I don't like this structure.
that's why we should talk about it. Okay, so you wanted to compare to,
One of those oxygens has too many electrons.
oh, I'm sorry, I put the double bond on the wrong side. Whoops. Thanks. Thanks for that. I just kept that there for a second because we were talking about comparing the two. And so, let's do BRF5. That an okay one to do?
Sure.
I haven't really done one like this. BRF5. So what would be the central atom? Bromine. And if bromine is my central atom, I got to put my fluorines all around the outside. How many total electrons do we have here? So we have 6, 5, 6, right? 6 different times the fact that we have 7 valence electrons on each, right? Is that correct? Because I have 5 fluorines and 1 bromine, and those are both in the same column on the periodic table. So they each have 7. So I have 6 atoms with each having 7 valence electrons. So that number is 42. I think a lot of you guys were saying 5 and then going to add another 7, which would have, or 35 and then add another 7. That'd have been fine too. Got us all to the same answer one way or the other. So then I'm going to add my electrons to the outside. So after I add electrons to the outside, will I have used up all of my electrons? How many electrons have I used?
40.
40, because I have 5 times 8. So I've used 40. So that gives me 2 more electrons. Where do those go? My central atom. So how many electron domains do I have? What's my steric number?
6.
So if I have 6 electron domains, what's my hybridization?
Oh.
I asked a different question than you thought I would. D2. sp3d2 is my hybridization. What would be my shape? Square pyramidal. And what would be my bond angle? Okay. A little less than 90 would be acceptable to say as well. Yes, sir.
Is there a maximum number of electron domains that have?
The ones I would expect you to see would be 6. I don't think you'll come across any that have more than 6.
And does that just have to do with like hybridization? Why?
It has a lot to do with hybridization because you get to a limit of where you can put electrons.
Okay.
And that will start to get to the limit of what the chemistry world understands about bonding. So that's kind of where we're working right now in research in the world, kind of figuring out what happens after that. But so that's way above where we need to be. But yeah. And then how many sigma bonds do we have? We have 5 sigma bonds. How many pi bonds? Good. Oops. And then pi would be 0. Okay, so then I want to look at my polarity. Would I say that this is a polar molecule or a non-polar molecule? Polar. So if you can kind of imagine it as my pyramid, right? It's hard to draw a pyramid, but if you sort of imagined it that way. And so we have my atom here in the center, and then my electrons kind of going around the outside. What? I try. And so my electrons are going to be ending up going out there. And remember, our lone pairs are here on the bottom. So it keeps all my electrons sort of towards the top of my pyramid. If you can even imagine it, it kind of goes up a little bit. So I should have asked you, but since fluorine is the most electronegative, hopefully you can establish that they are going out. So my molecule we see as being polar. If I were to compare this molecule to that molecule, which one do you think is going to have more polarity? Why would this one have more? Fluorine is the most electronegative. If we were to compare sulfur and oxygen's electronegativity, they're somewhat similar because they're still fairly close. They're both fairly close to fluorine. They're both fairly close to each other. So its electronegativity is a little bit more similar, whereas fluorine and bromine have a large difference in electronegativity. And so that's why this structure is able to happen in the first place, and that would apply.
So would it be slightly positive at the top or the bottom of your bromine?
It would be the negative, the positive would be to the bottom. Because remember your bromine's like on the inside of your structure, and then your fluorines are all around it here. Yes, ma'am.
What would like the polarity values like on something like
Something that's nonpolar. So like BH3. And so if we were to look at, I don't know if that's a great example. Let's do it. Stop, nonpolar. Okay, we'll go back to that. So imagine our electrons are going to be going, this is as much as I want you to be able to see, is that our electrons would then go 3 separate ways. And since they triangulate themselves, they're all going in an equal direction. So they're able to pull out separately. And so they share their electrons.
So it's non-polar.
Yes, ma'am.
So if, sorry, going back to that last question.